Hey everyone, this is our 13th lecture. We're talking about generalized linear models, or GLMs for short. GLMs are really sweet because they take what we've learned about regression and extend them to a lot of other situations that are different from what we've seen so far. Now that you can see that we can do interactions and nonlinear relationships in regression, we're going to make it even further, where you can do those same things in generalized linear models as well. So what do I mean when we're talking about generalized linear models? Well, first you need to understand that there's a lot of types of outcomes out there in the world. Not all are just continuous and nicely distributed like we've mostly worked with in this class. For example, we have dichotomous outcomes. An example of that would be smoker or non-smoker, depressed and not depressed. If that's our outcome, then one way to handle it would be logistic regression. That's a type of GLM. If our variable or outcome is a count, for example, number of times visited the hospital this month, then we might use something like a Poisson regression or negative binomial. If our outcome was ordinal, like a low, mid, high levels of anxiety, or even a Likert scale, then we could use an ordinal logistic regression. If our outcome is a time to event, like time until a heart attack, then we're going to use survival analysis, which is a very special type of GLM. We're not going to get into each of these into a lot of depth, but we are going to introduce the ideas of these so that you'll know where to look and how to use them. So consider this example where our outcome looks like it just has two values, 0 and 1. Everyone is either 0 or 1, and then we have an x that's continuous. What if we just use OLS in this one? So just our regular run-of-the-mill ordinary least squares, what we've been doing all year. Do you see any issues with this scenario? Are there any problems with it? Well, first, it's very clear that that line doesn't represent the data super well. Most of the data are up top or at the bottom. That line is basically nowhere near any of them. It also has a tendency, it doesn't show on here, but the line could extend beyond the highest point or the lowest point on these. So the line could go past 0 or it could go above 1. It doesn't look like those kind of outcomes are possible. It's also important that, do you think any of the assumptions would be met with this kind of model? In this case, it probably wouldn't. The assumptions would probably be violated in a lot of ways. So what do we do instead? Well, we can use a GLM, and this slide is trying to give you the gist of it, the basics of what a GLM really is. And a lot of it you're going to see looks just like regression, just what we've done before. So we model the expected value of the model in a different way than the regular regression would. So in here, the yi is still the regular outcome. That's just whatever our outcome is for each individual. But instead, we're going to wrap that up in this special hug, which is a link function. The link function is just kind of a transformation. It's going to change the outcome into something more like a continuous outcome so that the regression can work with it. On the other side of the equation, we have everything is just the same as regular regression. We have coefficients and predictors, and we have an error term, just like we've worked with before. So if we go back to the 0-1 situation where our outcome is 0 or 1, we actually can see what this does to the line. In this case, it turns it into more of an S shape, which is often called a sigmoid shape. So what we're going to be working with is now this curve. And this curve fits the data a lot better than the line did originally. And that's due to this link function. It's changing the way the regression sees the outcome so that the line can fit it better. What's cool is all this is happening while we're fitting the model. We're not going to do anything to the outcome. We're not going to make any adjustments, but it will do all this for us. So it turns out regular linear regression is technically a type of GLM. It's a GLM with a link that is just called identity, which just leaves it the same way it was before. And the distribution of our residuals is normal. So linear regression is a GLM with a link that is identity and a distribution that's normal. But if we go into something like logistic regression or Poisson or log linear or probit or these other ones, then the link actually changes. So for logistic regression, it's a logit link, thus the name logistic, and the distribution is binomial. So the link, the wraparound for our outcome is a logit, and the distribution that we assume for our residual is a binomial distribution. For Poisson, the link is a log, and then the distribution is Poisson. Log linear is similar. Probit regression uses probit. Beta regression uses logit, just like logistic, but then it assumes a beta distribution. So all of these are just like linear regression, but they make certain changes to make these potentially problematic outcomes, the distributions that they have, into something useful for regression. And now it's really important to connect the linear models and GLMs, the stuff we've used before, and these GLMs. I've already said that a regular linear regression is technically a GLM with an identity link and a normal distribution. But it's important to understand that model specification is similar, diagnostics are similar, simple and multiple, so you have simple logistic regression and multiple logistic regression and other GLMs. You can have continuous and categorical predictors in both, and the assumptions are actually similar. We'll find that there are certain things that we have to do to check the assumptions for things like logistic regression. But again, the assumptions are similar. We are going to want to consider the same things roughly for logistic regression that we would for linear regression. For example, we'll still want to consider a DAG. We'll want to consider what's a causal mechanism here. We'll want to consider the assumptions. We'll want to know, do we need a control for anything? Are there any extreme cases? All these things that we've learned so far in this class applied to GLMs as well. Now, a quick introduction to the most common GLM that you'll see in your field most likely, which is the logistic regression. And it's a particular type of GLM where the outcome is binary or dichotomous. The line is a sigmoid curve, and the line represents the predicted probabilities of a yes or a 1 value. So along that line, that's saying what the probability for each given x point of being a yes. So if you go to x equals -2, you're going to see a pretty low probability of a yes. It looks like it's below 10. It's a really small probability of being a yes. But as you get to, say, x1 equals 0, now we're looking at a predicted probability of over 60%. And then by the time x is equal to 1, it's nearly 90%. And so these are what are called the predicted probabilities. We're going to go into this a lot more in our logistic regression lecture. But it makes it, this transformation that's undertaken with logistic regression, it makes it so the predictions are never less than 0 or more than 1. That line will never cross above 1 or below 0. It will flatten out and never cross. And what's cool is it often matches how probabilities work. In a lot of cases, the probability may actually have this quick change at some point. There's some threshold where the probability is going to make a quicker change. So even when you're on the very far left of x1, even if you move a little bit, your probability doesn't change much. But at some point in x1, there's this change where your probability changes a lot. And that is often how probabilities actually work. That when you're in the extremes, making small changes doesn't really do much. But when you're in the core of it, making a small change may actually change the probability of a yes a lot. So if we pull it back to the link and the distribution, the logistic regression uses a logit link, which is technically the log odds. Now, when you think of odds, we're going to talk about this in a lot more depth in the logistic regression lecture. But it's just the probability divided by 1 minus a probability. That is an odd. That's the odds of something. And we just take the log of it, and that turns our binary outcome into a nice continuous variable. And that allows us to basically use regression just as we normally would. The only thing that's really different is that the distribution itself is binary instead of normal. But when we actually go to interpret something from a logistic regression, we have to understand that our coefficients are now in terms of the logits or the log odds of a positive response. So what this means is for a 1 unit increase in x1, there's an associated estimate, the beta coefficient, change in the log odds of the outcome. Now, because probably none of us understand what a log odds means, there's different ways that we actually can interpret these results. They're just small adjustments to get more information out. In this course, we'll go over odds ratios. This is probably the most common way to interpret results from a logistic regression. And really, it's just the exponential of the coefficient itself, and that turns it into an odds ratio. But note that these can be slightly biased, but they are still the most common way to interpret logistic regression output. We also can get the average marginal effects. These are less biased than odds ratios, but they're not as common, and they may oversimplify the situation sometimes. And then we also have the predicted probabilities, where we can actually look at where's the line at and talk about that. When we get into the logistic regression lecture itself, we're going to talk about these in detail. So for a quick example, let's say you've now turned to binge watching movies on Netflix because you've gone over some of the other shows that you've already binge watched. But you've come to see that many of the blockbuster films don't feature women in leading roles very often. You come across a Bechdel test. It gives a representation of women in fiction data set, and decide to examine whether budget, the numeric predictor, predicts passing or failing the Bechdel test, which is just a dichotomous outcome in the data. So first you just run a linear regression using budget to predict whether the movie passed the Bechdel test and get the following results. So this is just a linear regression, just what we've been doing before. And what this would say is there's a significant relationship between budget and whether or not they pass or fail the Bechdel test. When you're using this form, this is called the linear probability model. Now the outcome, that negative 1.6 to the negative 4, that represents the change in probability. So for a 1 unit increase in budget, there's that much change in probability in a linear way. But one of the things that we need to consider, so that does make sense, it's intuitive, and sometimes a linear probability model can work well. But one of the things we need to consider is we need to look at our residuals. And as you can see, they are not looking so great. So the residuals do not look good in terms of homoscedasticity, normality, and if we looked at other stuff, it wouldn't look good there either. So we're definitely violating some assumptions here. So you realize that because you have a binary outcome variable, that another option would be logistic regression. You rerun the model, and now using the GLM function with a family equals binomial, which we'll get into in the in-class activity, we now see that the coefficient is still negative. It's still this negative 0.001, and it is significant. But now that coefficient is in terms of the log odds. So for a 1 unit increase in budget, there's a negative 0.001 change in the log odds of a passing grade on the Bechdel test. So to actually interpret these, we can use log odds, odds ratios, predicted probability, AME, all of those. Again, we're going to go into much more detail later on. But if you're looking just at the log odds, then you'd say for each $1 million increase in budget, there's an associated 0.001 decrease in the log odds of passing the Bechdel test. Personally, that's not super meaningful to me. All that's telling me is that the probability is decreasing as you increase the budget. Now the odds ratios is just the exponential of the log odds. It would say for each $1 million increase in budget, the odds of passing the Bechdel test decreases by a factor of 0.999. Now, because we're going to go over these in more depth in a later lecture, I just wanted to have these here to help you understand that the interpretation, when your model gets more complicated, the interpretation tends to get a little bit more complicated too. But each of these, when you get down to it, become interpretable. For example, for the predicted probability, you can say when the budget is 50 million, the expected probability of a movie passing the Bechdel test is 54%. At a budget of around 300 million, the probability of passing the Bechdel test changes from greater than 50% to less than 50%. So as we're increasing this budget, our likelihood of passing the Bechdel test, which is saying more women are in leading roles, it's actually decreasing. So bigger budgets, we're less likely to have a reasonable amount of women being represented in leading roles. Then the AME, which I think is the most interpretable, but sometimes oversimplifies the situation. We would say on average for each $1 million increase in budget, the chance of passing the Bechdel test decreases by 0.02 percentage points. In other words, the probability decreases by 2. So if we were at 50%, if we increase our budget by $1 million, then the chance of passing the Bechdel test decreases to 48%. Again, these are just examples. We're going to have many more to come. But the idea is that when your model gets more complicated, you have to do a little bit more to interpret it. But that means that you actually can get a lot of information out. For example, here we already have 3 fairly interpretable ways to talk about what's happening in our data, which I think is fantastic to have that kind of information from a single model. Now, notably, there are other GLMs. So here I list Poisson, ordinal logistic, survival, beta, negative binomial. There's many others. All of them go with certain types of outcomes, like Poisson goes with counts, ordinal logistic goes with ordinal, beta regression goes with bounded outcomes. What you're going to be able to do after these lectures is be able to understand that I need to go look for a GLM that works with this kind of outcome, and then you will be able to figure out how to work with it. Because notably, it's going to be just like regression with a few twists to it. Our next few lectures are going to go over logistic regression, and then it's going to provide more in-depth information on some of these GLMs as well. So for additional resources, we have 4 here. They're all great. Take a look at each one. These can help you understand GLMs a little bit better and how they work, including some very specific ones. I think GLMs can be overwhelming and complicated at times, but they can be extremely useful. And once you really get to know them at their core, you see them as just special cases of regression, and they become much more friendly. So please take a look at these, reach out if you have questions. And in the next unit, we'll go into a lot more depth into these individual GLMs.